My name is Dylan Satow, and my presentation is the effect of pure water concentration on a Cherenkov detector's accuracy when detecting astrophysical neutrinos. And to start off with, we should say answer the question of what is dark matter. We know it's most likely composed of WIMPs, which is weakly interacting massive particles, and that's just the common acronym to show it. And what that basically means is that the particles don't really interact very much with regular matter, the matter we see every day, which is kind of self-explanatory by the name. But yeah, so if I got hit by a massive dark matter particle, I wouldn't realize it. The main way we know they're there is by gravity. And dark matter is scattered throughout the universe, and it has a distinct gravitational effect on visible matter, as I touched on earlier. And it is thought to make up 20% of all matter, and it's a lot more significant than visible matter, and that makes up less than 5%. And so those are our current theories on that. And then why is it important? Right now, there are not that many direct applications of dark matter onto like everyday life, but the main purpose of studying dark matter is to improve our knowledge of the world and the standard model in hopes of kind of creating one theory of everything, and hoping that eventually maybe it'll help contribute to that and just understanding the phenomena around us more. And by improving our knowledge of physics, it opens the doorway for all new kinds of inventions, which it's kind of many of the formulas that have been derived from that have gone on to like make really amazing inventions. The key terms are a photomultiplier. It takes in an input of photons and outputs electricity. So basically, if light hits it, it'll give an electric pulse denoting that light hit it, and it's just a signal basically. And then a Cherenkov radiation is that the radiation when an electron or a muon travels through a material medium faster than the speed of light, and that may sound kind of weird, but it's only faster than speed of light in the medium. It is still slower than light would be in the vacuum, so it's not like breaking the laws of physics. And a neutrino is a neutral dark matter particle, so it's a neutral charge, and it has a mass close to zero, and it interacts weakly with other particles, like because it's thought to be a WIMP. And that like it's when I say mass close to zero, like it's very close to zero. For a long time, people thought it had no mass. It's much more insignificant than an electron. And neutrinos, we don't think they account for all dark matter. It's just a fraction, but we do not know like what else really much about the rest of it. And the primary articles for the background are enhancing neutron detection capabilities of a water Cherenkov detector. And yeah, and then this shows that like even though the title states neutrons and not neutrinos, it still focuses a lot on neutrino detection and dark matter detection. It just kind of shows how they can be applied to other fields. And it shows that the methods used to detect dark matter neutrinos could also be applied to visible neutrons, or neutrons, yeah, to like visible matter neutrons. And it uses both distilled and aqueous solutions of NaCl as the detection volume. It doesn't only use water. And the main reason I chose it is because it got really in depth into how the Cherenkov detectors work, and it kind of helped me to improve my understanding of it. And it shows the extent to which Cherenkov detection can be used for neutrinos. So it's like it kind of shows its limitations. And the next article is search for reactor neutrino directionality using a lab-based GD-loaded liquid scintillator detector. And this basically shows that it uses liquid scintillator as opposed to pure water, which is basically just another. It's kind of has a similar effect. It's kind of a similar type of thing. It's just a different detection liquid. And because Cherenkov radiation cannot be immediately detected, the inverse beta decay calculations must be applied to the data. So it's kind of like you need to do a lot of math to like process the data basically. And then it shows that the application of the Cherenkov detector technologies onto large liquid scintillator detectors, and it was environmentally friendly. It wasn't polluting or anything. And the last article is atmospheric Cherenkov telescopes as a potential veto array for neutrino astronomy. And it uses an ice cube neutrino observatory very effectively. So that's not an actual ice cube. It's just the name of an observatory. And it separates astrophysical neutrinos from background neutrinos. So it's not just like the neutrinos around us, kind of. It's like the ones coming from space. And it proposes a cost-effective memory for separating different kinds of neutrinos. And the more telescopes you have is better, and it gives you a better result. And it kind of shows how physics is constantly becoming more effective and cheaper. And like the reason it's significant that they were able to get a cheaper method is that it means that they can do it at a much larger scale with the same budget. So it means we can figure out a lot more without having to spend a lot more. And then getting on to my problem statement, it is how does the pure water concentration of a Cherenkov detector impact its accuracy? And the hypothesis is that a Cherenkov detector's accuracy will increase if more pure water is added because it allows for more surface area in which neutrinos can collide with the regular particles. And the goals are to understand the role of water in a Cherenkov detector. So to really get a sense of how, like, what it really does to have water in the detector, and what it really, really how much of an impact it has when you change that amount of water, and like if it's really necessary to add a lot more water to the solution, and to gauge the most cost-effective amount of water necessary for the detector to function. So it's kind of like whether or not there's like if it's kind of like logarithmic, where it kind of gets less effective as you go on. And then the funnel effect, the first article, Enhancing Neutrino Detection Capabilities of a Water Cherenkov Detector, allowed me to understand how the Cherenkov detectors work at a basic level and show how they can be applied all over physics and do a lot of different things. And the search for reactor neutrino directionality using lab-based GED-loaded liquid scintillator detector showed the advantages and different disadvantages of different types of dark matter detection, which ultimately led me to choose the Cherenkov detection methods. And atmospheric Cherenkov telescopes has a potential veto array for neutrino astronomy, and it led me to ponder like how drastically differing amounts of water affect accuracy. So if there's really a big difference between 100 gallons and 50 gallons, and if it's really that necessary to have 100 gallons. The methods were that the super Kamiokande, that would be the primary location at which we'd want to do. It's the biggest one in the world, but obviously that in a real life setting that wouldn't really be possible. So a more cost effective alternative would be usable. And then if we're using that, we need 50 tons of ultra pure water. So it has to be really distilled, super clean, and we need a lot of water. Yeah. And I chose to use water, not scintillator liquid. And the procedure is to set up and staff the Cherenkov detector, add 10 tons of water, and then begin the detection process, and then analyze the photomultiplier after, and then compare the results to what is expected of that water level, and then find the difference between the actual and expected values, and then wait 24 hours to ensure that the time of day isn't affecting it or anything. And then repeat steps 2 through 7 4 times, adding 10 tons of water to the Cherenkov detector each time. So what this would show is how what we'd mainly be looking for is the accuracy of it and comparing it to what it should, how many neutrinos should be bouncing around in there, and if we had a proper amount of water to like test it and see if adding that 10 tons of water really continues to have a linear effect on like how accurate it gets, or if there's a certain point where it kind of caps off after that. And then steps 1 and 3 are all standard neutrino detection steps that would be used in all experiments involving the detector. And then step 2 is the adding of the liquid medium used and directly ties to the independent variable, which is that like how does altering the amount of water affect it. Steps 5 and 6 are both used to show how off the measurements were and will be later used to calculate like the percent error. And then we can compare that between all the different values. And then step 7 is to ensure that the time of day is not impacting the measurements. And then the control variables are the time of day because we're waiting 24 hours. The weather, and if the weather is different than the starting date, we may wait one more day because 24 hours is already a lot. The location, it would stay consistent. And the type of liquid used, because we're only using pure water. We're not using aqueous solutions or anything like that. The variables are, the IV is the amount of pure water in tons, and the dependent variable is the accuracy of the detector. And then the related results are that this first one shows how like the it shows how the protons or the positrons and the electrons, it shows how the positrons are actually traveling like backwards in this. They're like slightly backwards, not by a lot. And it shows that like Um, Sorry for that. Yeah. So then this result, which comes from the search for reactor neutrino directionality using a lab-based GD-loaded liquid scintillator detection. Um, what this shows is that basically the positrons were actually traveling like backwards a little bit in this case. So then it basically shows that like the second the neutrino entered, the electrons and the positrons instantly annihilated each other in a reaction of pure energy. So then it basically just shows that it was able to detect all the stuff that it wanted to. And then this shows a relationship between the incoming neutrino and the direction of the neutron it was measuring. It's from the same article, and it was the one where it applied it to neutrons to see if it could work. And it seemed, and there was a real correlation between the incoming neutrino and the neutron. So take what you will with that. It's kind of yeah. And then the impact is that our proposed study could allow scientists to have a better experimental understanding of how much surface area is the most cost effective when detecting neutrinos. And yeah, that's my presentation. Thanks for watching.